Okay, this is remediation for Coulomb's law. Let's say we have two charges here, and I'm going to divide this up into three regions, and we're going to find out what the electric field vectors are from each of these two charges along this axis that contains the two charges. So charge 1 is right here at 0 meters at the origin on the xy axis, and charge 2 is over here on the x-axis some distance, positive distance away. Let's say charge 1 is positive and charge 2 is positive. If we put a test charge, a positive test charge, let's say over in region 1, the electric field vectors kind of look like this. Let's assume charge 1 and charge 2 have the same magnitude. So let's say both 2 coulombs or something like that. Since charge 1 is so much closer to the test charge than charge 2, because of the inverse square relationship, its vector is much bigger. Now let's say charge 1 is positive and charge 2 is negative. Same magnitude though, so 2 and negative 2. Now you'll see that E field vector 2 now points towards charge 2. So the negative charge tries to pull that positive test charge closer toward it, and the positive charge of Q1 tries to push it away. If Q1 is negative instead and Q2 is positive, then it just reverses those two vectors. And then finally, if they're both negative, then they both point to the right. That's in region 1. Now let's do the same thing for region 2. So now we're going to put the positive test charge. Let's say it's a little closer to Q1 than Q2. Again, keep in mind Q1 and Q2 have the same magnitude. So given that it's so much closer to Q1, the E field vector from 1 is so much bigger than E field vector from 2. Both of the positive charges, Q1 and Q2, try to push this test charge away. If Q2 now is negative, now Q2 will try to pull it towards it. So both E field vector 1 and 2 point in the same direction. If Q1 is instead negative and Q2 is positive, then instead of being pushed to the right or pulled to the right, now it's going to be pushed and pulled to the left. E field or Q1, which causes E field vector 1, will be pulling it to the left. And Q2, which is positive, creates E field vector 2, which kind of pushes the test charge to the left. Now let's say they're both negative. In that case, E field vector 1 is Q1 is trying to pull it toward itself, and Q2 is trying to pull it toward itself. But since Q1 is so much closer to the test charge than Q2, its E field vector is bigger. Okay, now finally, region 3. Let's put the test charge way over on the right-hand side. If both of the charges, Q1 and Q2, are the same magnitude, and they're both positive charges, then both the E field vectors will point to the right. Both charges try to push it away. But Q2 is so much closer, that's why E2 is much larger. If now Q1 is positive but Q2 is negative, we just simply reverse the direction of the E field. And so now Q2 is trying to pull the test charge toward itself. Now let's say Q1 is negative and Q2 is positive. Then E field vector 1 is going to be to the left because Q1 is trying to pull it to the left. And E2 is going to be to the right because Q2 is trying to push this test charge to the right. And then finally, let's say they're both negative. Then they're both trying to pull the charge toward the left, both Q1 and Q2, since they're both negative. And that means E field vector 1 and 2 are both in the same direction to the left. Okay, so now let's consider all three regions. Notice that in the white regions, the E field vectors point in the same direction. In other words, the net electric field in region 1, if they're both positive, or in region 3, if they're both positive, is in the same direction. In other words, the E field, the net E field, would never be negative. Same is true if they're negative charges, except the direction of the E field would be reversed. They never cancel. If we have a positive and negative charge, so opposite polarities, then in region 2, those E field vectors would add together, and they also do not ever cancel. The only time that the E field vectors would ever possibly cancel is if you find just the right location, and I have those in yellow. So that's when they're in opposite directions. So for instance, let's say we have two positive charges Q1 and Q2. In region 2, the E field vectors are in opposite direction because they're both trying to push this charge away from themselves. So if they have the exact same magnitude, let's say both positive 2 coulombs, then the net E field at a position exactly in between them would be 0 because those two vectors subtract away from one another. Same is true as if both charges are both negative, because then they're trying to pull it toward one another. And so right in the middle, if they have the same magnitude, -2 and -2, then they would cancel. Now, if they don't have the same magnitude, let's say one's 2 and one's 3, let's say 2 coulombs and the other one's 3 coulombs, or -2 and -3 coulombs, then it's going to be a little bit closer to the smaller magnitude one, because the other one is going to kind of dominate. But there will be some region in between them that it will exactly cancel. What about if they have different polarities? Well, the only possible regions where they would cancel would be in region 1 or in region 3. It really depends, though, about what the magnitude of the charges are. For instance, let's say one's positive 2 coulombs and the other one's -2 coulombs. There would be no place then, because let's say in region 1, you're closer to the Q1 than you are to the Q2, but they have the same magnitude. So always the E field vector 1 is going to be larger than the E field vector 2. And so they never cancel. However, if Q1's magnitude is smaller than Q2, let's say positive 2 coulombs for Q1, and let's say -3 coulombs for Q2, then there is a place where they would cancel over here in region 1, because even though it's closer to Q1, because the magnitude of Q2 is bigger, there's a place somewhere over here where they would exactly cancel. If instead Q2 was the smaller one, then it would be over in region 3 where they would cancel. So, and the same is true as if you reverse their polarity. So that's why I've made it kind of a lighter yellow here. It could possibly cancel. So if they have the exact same magnitude, let's say 2 and -2, there's no place where we would cancel. But in any other situation where they're not exactly the same, so let's say 2 coulombs and the other one's -2.1 coulombs, then there will be exactly one place where we would cancel, and it's going to be closer to the smaller magnitude one. So in the example I just listed, it would be closer to the 2 rather than the 2.1. So that are either put in region 1 or region 3, wherever that is. Okay. So let's try an example. Let's say we have these two charges, 3 and -4 microcoulombs. And the positive 3 is at the origin, and the -4 is some distance away, positive 0.8 meters on the x-axis. And we want to find a location where the electric field is 0. Well, there is exactly one location because they don't have the exact same size. It's not 3 and -3. If it was, then there would be no location. And since one's positive and one's negative, it's going to be either in region 1 or 3, and 1 is closer to the smaller one. If they would have been both positive, let's say 3 and positive 4, then the location where it's 0 would have been in region 2. In this situation, though, it's going to be in region 1. Let's call the charge at the origin 1 and the charge at positive 0.8 meters charge 2. I know that they're going to be a place where the E field cancels somewhere in region 1, so I'm going to say that's point P, and I'm going to draw on my E field vectors. From charge 1, it points to the left, it's pushing away, and from charge 2, it kind of pulls it towards it. and at some location they cancel. They're exactly equal, they balance. So I can write an equation since they balance. E field 1 equals E field 2. We know the E field is given by KQ over R squared. So it's going to be KQ1 over R1 squared for the E field 1 and KQ2 over R2 squared for charge 2. Since there's a K on both sides of the equation, that will cancel out. Also notice they're both microcoulombs, so times 10 to the -6 on both sides of the equation. That will cancel out. For E fields and for forces, you never put the polarity in. In other words, you never put the negative sign in. For R1, it's going to be some distance away from 1, so let's just call that R. From charge 2, so R2 is going to be R plus that distance of 0.8. So let's go ahead and plug that in. And cross multiplying and simplifying, we get 3R squared plus 4.8R plus 1.92 equals 4R squared. You should go ahead and slow this down and replay that and make sure that you understand the math. You should understand the math given the high level of math that you're in right now. But based on my experience, this is where students often falter. So make sure that you understand this in its entirety. Now let's go ahead and solve this. I'd have R squared minus 4.8R minus 1.92 equals 0. Solve this quadratic, we get two values for R, 5.17. So remember R is some distance measured from 1 that it's over to the left. So 5.17 to the left, or it could be a distance of negative 0.37. So negative 0.37 to the left would actually be 0.37 to the right. Well, that can't be it, so that's out. We know it has to be in region 1. So the answer is going to be, the location is at negative 5.17 meters. Given that charge 1 is at the origin, I have to remember that to the right would be positive and to the left is negative. So if I want to know the location, it's at negative 5.17 meters. Okay, so you should be able to do the SWIC now, no problem.